last time we did what do you call it, fluid statics, and then we did a hydrostatic equation, right? I advise that anytime you do that, like you solve further questions to get the understanding very well. Okay, this time we are doing fluid flow. Okay, for this particular session, we are doing what we call the Reynold experiment. What the Reynold experiment does is that it helps us to get understanding and then produce some values that are used in analysis, right? So we call these numbers Reynolds number. I think using at this, or if you see this, is the same thing, right? Reynolds number. What it's saying is that when you have a container like this, right, and then you attach a jet here, right, like something like a tap or something, and you allow the water to flow. When we cut here, like something like that, so it's like we bring it this way and then we show the cross section here to see what's happening, how the fluid is flowing inside, right? Here's a case where they place some dye here and then the dye is flowing through the water. What the analysis does is that it helps us to see how another fluid or another particles are flowing within that particular fluid. Okay, all this experiment was done by this guy, and then we have laminar and turbulent flow. Generally, if you remember the plywood, like you've seen a plywood before, you look at the side, you see something like this, like a plywood like this, right? But if I want to look at this side, you see this, and you see like something like a wood that have been put together to form the whole plywood, right? So we say it's laminar, right? Laminar. In what do you call it? In composite, at times you see something we call laminated material, something like, or in glass, you see laminated glass, right? Just by the way to give the understanding. What we're saying here is that these are different scenarios. That's what we're saying. All these are cross sections, right, of the tap here. You can. It's like we've made a dye pass through, and then we are looking at what's happening within this region, right? So this region is what has been cut, and then we are seeing it here in this section, right? So this is what we are seeing. So you see in this particular case, the dye passed through straight, right? For this particular case, the dye, straight, and then turns a bit here, and then here it moves straight, and then you see some turning up and down, right? Yeah, these are different scenarios. And then in this particular case, you see here where it's flowing straight forward, we can see it's a laminar flow, right? And this particular one here where we haven't straight, and in the end is having some wavy nature. Here we haven't straight, and then we end up getting the wave here. All this region we can see we having some kind of laminar flow, right? It's flowing very straight, like in line. But here you see it's like turbulent, like waves, right? We're having some wave in each other side. So you see, I talked about Reynolds number can be written this way or this way, right? There's a formula for it. So as I was saying, the flow depends on the fluid they are trying to flow through, right? So when you look at this side, here, the reason why we're using the dye is that if we are to use only the water alone flowing through this side, we won't see what's actually happening, right? When we can't see it, right? So we use the dye to show the movement within that particular fluid. Okay, the dye makes it what do you call it, visible. So we say the dye is a tracer within that particular system. Okay, yeah. So in the Reynolds number, that's what we have. So we are seeing that whatever that's happening within that particular flow, like this, and then we have this flow, even if it's straight or wavy at some point, all depends on this, right? But then from all the experiment that Reynolds did, so you see initially we are like Reynolds experiment, right? So the experiment is what gives out these numbers, and most of the times these numbers are there, and then there's a range. And the range is that when this Reynolds number, right, is greater than 2, is it 2 1? Yeah, 2100. Generally, we are seeing that the flow within a particular system is turbulent, right? So it's wavy. But if it's less than this 2100, we say it's laminar, right? So when you look at it in this case, you can see that everything that's happening, if this A, this B, this C, and this D, you can see that the flow here is laminar, here is laminar, there's a bit of turbulence, and here is turbulent, right? Fully turbulent, or this we say fully developed turbulent flow, right? And this we can see developing turbulent flow. Yeah. So that's what I'm saying, that but it makes sense. Let's go through this and see what's happening. If I have let's say a container like this is a container, and then we're having the tap here and it's flowing at this side, right? And we're having the dye flowing through this side, right? And dye flowing through this side. It makes sense to say that if this particular dye here is able to pass through this straightforward, the moment it starts having some wavy nature, we are seeing it's having some encounters, right? As in disturbances. Yeah, then we are just trying to get an understanding, but like it's very crucial that I remember this equation, right? Reynolds number, this and then this, they are the same, but we derive why this one gives us this. But let's develop and see the reason why the equation is that way. So like if this die here, this is a die, right? let me make it red so that it's much more clear per what the road did the other time in that diagram. So like if this die here is able to, if this die is able to flow through this one straight, like straight like this, we can see that it's not encountering a lot of disturbances. So right, we are seeing that. Yeah, so you see that if it were to happen that we have like this flow in this region, so then again the discussion that we are doing every discussion here, like if we were to have a line here like just straight like this, you could see that it's not straight though, but like just imagine straight. Right? Let me do it this way. Okay, if I were to have something like this, I'm coming. Try and clean this up. The understand is very important because like you end up using this concept everywhere you go. Okay, so it's very important. That's why I'm trying my possible best to make sure that we get this one. Okay. Yeah, it's working. Okay, so let's see if the flow were to be in this way. Let's see something like this, right? In this region. Then again, I'm emphasizing on this because we are doing a study here. If the flow were to be something like this in that region, right? I could say that like it's laminar, right? And then initially when we're here, I was like per his research and stuff, when the Reynolds number, let me write it again. Let me write this. When the Reynolds number RE or NRE, let me do this. Then again, I'm stressing on this because it's very important. Like, yeah, you see it a lot. Like the random number, let me write this. If you have something like this, let's see RE, which is I said initially the same as this NRE, right? If you have to have, I said initially that if it's greater than this 2100, we say it's turbulent, right? Per his experiment, Reynolds experiment. But if you have a less than this 2100, we say it's what laminar, right? Then you see that. Let's go back to the equation. When you look at the Reynolds number equation again, this is what you see, that the more these are the ones that will make the number get bigger, right? The Reynolds number getting it bigger, right? And this is what makes it smaller. So when we look at it again, if you are to have it flow like this, meaning it's having less hindrances, right? And then less hindrances mean that the particle, what do you call it? The fluid that we are flowing through is less dense, right? Less dense, so like the more the density goes up, the more laminar we'll get, right? So instead of getting the straight line like this, we'll get something like this and maybe flowing wavy, right? So the more the density goes up, the turbulent flow goes up, like the chance of the flow within a particular field being turbulent goes up, right? So then again the velocity, and then this here is what's the name, the diameter, right? So then again, if we are doing our discussions here, the diameter of concern will be from here to here, right? Yes, the diameter of the tube. So that's how it goes. But then you see that we have this and then it's rewritten this way, right? Okay, let's go through this. So it's like this D is still here, this D is still here, this V is still here, right? So this V is also still here. This V is still here. So the only thing is this and this, right? So we are saying that this V here, sorry, this micro sign here is kinematic viscosity and this one is dynamic viscosity. It's like this is the relation between these two. That's why this the rho over this micro sign here has been replaced with this V, right? So we are seeing that this V here at times written as just V is equal to kinematic viscosity over density, right? So if you want to replace, we are in the equation there, we don't have it this way like this over this, we have it the other way around. So meaning that if we want this, what's the name, if you want this density over this one, we end up getting 1 of V, right? So that's what's here, just that. But then again, this what's the name, this equation is very important. Try and understand it. I was just giving a gist here, but try and understand it and then know these values too, that what is greater than this 2100 turbulent, less than this 2100 laminar. Okay, so it's been said here again, right? So we have a laminar flow, right? Laminar less than this, right? So you see RE or NRE, if you see them, they are the same thing. So you see turbulent, right? More than this. There's the mean velocity. Yeah. Okay. Initially, when we started, you see, I was drawing a lot of stuff like this, right? Where I was having. Let me go up and see. If I still have it here. The more it's having some kind of flow in this particular diagram. This is not what's the name, flow itself, but it's what we call the velocity profile. So you see, I was drawing stuff like this. Where is it? Yeah, like this. So you see, it comes, it takes what do you call it, a continuous smooth curve, and it goes and it comes back, right? So you see, that one is laminar. You see, this one just goes straight, like kind of like straight, and then it bends deeply, right? Turbulent flow. Then again, the number that we discussed initially, the Reynolds number, is what describes the whole process, like how these stuff are. Yeah, so then streamlines. The streamlines, you see, initially we're like, when you look at this particular diagram, where is it? We're using a dye in that one, right? Because like if you're trying to look at whether the flow in the particular fluid is laminar or turbulent, you can't see it alone. So we use what we call a tracer. So in this case, see, they are using a dye, right? So if we are to look closely, this one is like this part. You see that? Let me clean this so it's more clear. See, the jet here just drew just one line of that particular dye, right? But it's not always the case. When it comes to streamlines, it's like we are having multiple traces tracing different lines, right? Different lines. So it's like dye particles traveling different lines, right? Just the same thing, nothing different, right?